So let's see if we can't find the derivative of sine and cosine. I'm going to derive for sine, and then you're going to try and find it for cosine on your own. We have here some reminders. The limit as delta x approaches 0 of sine of delta x over delta x, or you could also say x approaches 0, x over x, or h, whichever you want to pick, is going to be 1. That's review from the limit unit. And then for the other one that was a corollary to this theorem, that's equal to 0. We're going to need that a little bit in our derivatives here. So we're going to take the derivative with respect to x of sine of x by using the limit definition. So the limit as delta x approaches 0 of sine of x plus delta x minus sine of x. So that's f of x plus delta x minus f of x over delta x. And then we don't really have many other options then we can't factor, we can't do anything other than, right now you get indeterminate form. So we need to use a little bit of expansors. You have to review a little bit from hopefully pre-calc. Remember, sine of a plus b is sine of a cosine of b plus sine of b, cosine of a, like that. So that's what we're going to apply to this piece right there. So we are going to write the limit as delta x approaches 0, and then expand that entire thing. So I'm going to maybe pick a different color. Ooh, that's a little bit crooked. Let's try that again. Expand that out. So then let's do that in blue then so you can see it. We're going to do sine of x cosine of delta x plus sine of delta x cosine of x minus sine, I'm going to go back to red for that one because I wanted to just do the expansion in blue so you could see where that's coming from. Sine of x over delta x, like so. All right, so we're going to do a little bit of shifting around. A couple of things that I notice is that if I grouped this with this one right here, I could factor out a sine of x. And if I factored out a sine of x, it would look very similar to the one I have up here at the top, right? It might have switched to sine, but we could always factor out a negative if we had to. So if I factored out a sine, maybe we could get close. So let's see here. We are going to get the limit of delta x approaching 0 of, so now the part that I'm going to use is I'm going to just leave the part I'm not going to use, sine of delta x cosine of x. And then I'm going to group together the sine of x cosine delta x and actually factor out the sine of x. So that means I'm going to write plus sine of x and then do cosine of delta x minus 1. So right now, what is highlighted in yellow corresponds. I just group them together, and then that's all over delta x, like that. Okay, it's almost looking like the one up here at the top, except it would probably be better if I took out a negative, then it would match exactly. So if I took out a negative one also, it would switch these two in there. And I have two terms essentially. So in blue, this is my one term in the numerator, and in yellow is my second term. So I'm going to separate the limit into two parts. So I'm going to do limit of delta x approaching 0 of sine of delta x cosine of x over delta x. And then plus, I can do the second term as a separate limit, delta x approaching 0. But I'm going to factor out a negative so that it will match what I have up there. So I'm just going to write negative sine of x 1 minus cosine of delta x over delta x, like that. So right now, what I see is this. For the left one, this right here that I'm highlighting in blue, if I took the limit as delta x approaches 0, that is going to be 1. And the cosine of x does not have a delta x in it, so it's not affected by the limit at all. So I'm going ahead and simplifying that. So I'm going to write the limit. Oh, I'm simplifying. That means I'm going to take the limit. So the blue part is going to be 1 times cosine of x. So just to see what corresponds, that corresponds, right? And then over here, again, I'm going to do, maybe I should pick a different color so it doesn't get mixed up with everything else. What should we pick? I am going to pick pink. Well, maybe pink is not good with red. Let's do green. Green. This one right here, I'm going to group that together. And I can also see that, sine of x doesn't have a delta x in it. So that's not going to be affected by the limit at all. So really, I end up with plus negative sine. So I could make it a minus. That would probably make more sense here. Minus sine of x times, but what I highlighted in green, when I apply the limit up there, we've proven earlier, is equal to 0. So that means that this is going to just be 1 times cosine of x, which is cosine of x. So in other words, the derivative of sine is cosine. And now that we've proven it, you can use that as a rule. I want you to try to do the proof for cosine on your own right now. It's done very similarly. You're going to start out here. You're going to do d dx cosine of x. Like that, and then apply the limit. Hopefully you were able to prove to yourself that the derivative of cosine of x is equal to negative sine of x using the limit definition. And that's the theorem. We just did the proof. So we did it a little bit backwards. Instead of giving you the theorem first and then proving it, you derived the theorem, and here we have it. So do the proof for cosine, we just did it. And then we have example 8, find the derivative for each of those functions. So all you need to do is know the rule. And we have a constant multiplier for the first one, so we have y is equal to 5 times the derivative of cosine is negative sine. So negative sine of x, oh, I forgot to put the derivative there, prime, is equal to negative 5 sine of x. Done. Again, maybe this would be helpful to rewrite as 1/6 sine of x, and then go from there. So we got do y dx, or you could write y prime is equal to 1/6 cosine of x. For the next one, there's just 2 terms. You just have to remember to do those 2 terms separately based on the difference rule for derivatives. So y prime in that case is going to 1 minus 3 sine of x, but it's going to be negative sine, so that changes that to a plus. Try the next one. Hit pause and then try it afterwards. Okay, that's example 8. The next piece is the derivative of an exponential function. Just some things that you definitely need to review. We talked about it earlier this year, that the definition of a limit is, or excuse me, not of a limit, the definition of Euler's constant is going to be the limit as n approaches infinity of 1 plus 1 over n, all raised to the n. But you could also, there's an alternate definition for e, which is, I'm going to use a substitution. We're going to let x equal 1 over n. So I pause the video right now and then rewrite, see if you can rewrite it. Let's see if we agree. because we practice doing substitution like this. Okay, so now that you're back, this is the alternate definition of, oh, I wrote n, I meant x up here. That right there should be not n, but x. Those two are equivalent. Here, plus there. It could just approach 0, but it works for if I'm doing a straight conversion over like that. It's also true in the negative direction, so that's why this could have a plus minus there in each case. So that's why it could approach 0 from both sides and you get the same thing. But what that means is that we can use delta x instead of x, for example, and substitute, and this is our definition. If you then can solve for example, I want e to the delta x, raise both sides to the delta x. Then that means, tell me, if I know that this is true, right? That this here, as delta x gets very small, will be approximately e. So I'm going to then solve for e to the delta x, provided I know that delta x is approaching 0. So if I'm solving for that, I'm going to raise both sides. Approximately e here. Raise both sides to the delta x. So that means then that e to the delta x is going to be approximately, provided that the limit of delta x is approaching 0, e is going to be approximately or very close to 1 plus delta x, like that. Okay, so now we're going to use the limit definition. We're going to try and find the derivative of e. So that means e to the x. There's a typo again. This needs to be e to the x. I'm sorry. So here, let me change that in there. E to the x. You know I'm always good for a few. To the x up there. Let's change that there. So we're finding the derivative with respect to x of the exponential function e to the x. So limit as delta x approaches 0 of e to the x plus delta x minus e to the x over delta x. And that means I can rewrite this, the limit for the power rules here, I can rewrite this as e to the x times e to the delta x minus e to the x over delta x, which is then going to equal the limit as delta x approaches 0, factor out the e to the x. So then I'm getting e to the delta x minus 1 over delta x, like that. And I just discovered, provided here that it's delta x is approaching 0, which it is in this limit, I know that e to the delta x is approximately 1 plus delta x. So I'm going to go ahead and substitute that in. So we get the limit as delta x approaches 0 of e to the x over, okay, 1 plus delta x and then minus 1. Because just so you can highlight here, this one is this right here, right? Which is this right here. So I substituted that in, and we get that all over delta x, which is then going to equal the limit. I still haven't applied the limit yet, by the way. Delta x approaches 0 of e to the x times, now the ones cancel out. So I'm left with a delta x all over delta x. Those two cancel each other out, and now we really don't have a delta x left over. So when I take the limit as delta x approaches 0, it doesn't affect e to the x at all. So that's just e to the x, which is really cool and neat that e to the x is actually itself. When you take the derivative of e to the x, it just becomes itself. So when I then do examples of that, f prime of x, and here's the theorem, we just proved it, we did it backwards, we did the proof, and then we concluded that that would be the case. The constant multiple stays the same, and then the derivative of e to the x is just e to the x. Done. F prime of x. Now you try b and c. Hit pause, and then do b and c and see if you agree with me. All right, there we have B, and C. And that's it.